10.1, so we'll start with this. We'll imagine a particle moving along a curve. They call the curve C. So imagine a particle moving along a curve C, where it might look something like this. Now, I think of this when I see this little curve, and you don't have to draw this exactly like I've drawn it, and they gave something kind of similar in the book. So I got this curve, and I think of, maybe I'm looking down at the cement and I've seen a little snail or a bug. As they crawl around, they leave this trail behind. That's what this reminds me of. Last semester, one of the grad students gave a talk on this, and he gave that bus route, which is probably better than my example. Okay, he used the bus route as an example, but I got this curve, and as I'm looking at the curve, that's on the XY axis, I can look at it and say, this is not a function in terms of how you define functions in high school. C is not a function of the form y equals f of x. Why is it not a function? What test? Vertical line test. So it fails the vertical line test. But if I look at the ordered pairs on this curve, the XY pairs, it is possible that, again, I'm thinking of maybe a snail. It's possible that the position of the snail at time t would be a function. So we do this. We define the x and y coordinates of the particle as functions of time t, and we write x equals f of t and y equals g of t. And then if I look at time as the independent variable, that would be a function. Equations written like this, these are called parametric equations. So I'm going to write that next. Equations in this form, x equals f of t, y equals g of t, are called parametric equations. And the curve C is called a parametric curve. I'll just use C, but you could use whatever you wanted to call it. The curve C is a parametric curve.